Okay, so you should have drawn a graph from either your results if they look good, or you can use this little set of results here. So this is just our voltage in this column, and this will be our average current in that column. And if you plot a graph of V against I, your graph should look something like this. So what we have to do is draw a conclusion for why our voltage and current behave like that for a bulb. So let's start off with our usual first sentence, which is, as the voltage increases, our independent variable, what does the current do? And we can say the current also increases. Our next sentence we then usually describe, is it a straight line graph through the origin? If so, we'd say it's directly proportional, and we can see this one isn't. So we can say the graph is not a straight line through the origin. So voltage and current do not obey Ohm's law. Okay, they are not directly proportional. The next step is trying to explain why then. And we have to go into this in a little bit of detail to look at it. The first thing we can do is we can look at the slope of this graph. So if we remember from Ohm's law, V equals IR, therefore R equals V divided by I. And with V on the y-axis and I on the x-axis, that means that R is equal to the gradient. And if we look at the gradient here, we can see when the voltage is low, the current's low, and the gradient is quite shallow, okay? Which tells us that the resistance is low. So here we can see that the resistance is low. But meanwhile up here, the gradient is steep, therefore we can tell the resistance is high, okay? And in fact, we could work out the resistance at any point by kind of taking a reading for voltage and current and subbing them into that equation. It's not quite the right way to do it. Really, we should be drawing tangents, but we can get a gauge of it by doing that. So what we then really need to explain is, well, why? Why is the resistance higher when the voltage is high than when it's low? Because that's not the case for our resistor. It was a straight line through the origin, the resistance was constant. Although in Ohm's law, the final bit says as long as the temperature remains constant. And that's really the clue here. Because if we look at our bulb and we kind of just describe our other observations apart from the readings we were taking, we could see here that it was bright and it was dim. Now, why was it bright? It was bright because the little filament inside the bulb, that little thin wire, was glowing red hot. So the wire was hot there, but here, down at this point, it's cold. So next we want to try and link, well, why does the fact that the wire's hot mean its resistance is higher? And we kind of have to think back to last year's topics, but if we imagine the particles inside a solid, okay, when it's cold, those particles don't move much. They hardly vibrate at all. However, as it heats up, these particles begin to vibrate. And if they're vibrating, it's harder for them, it's harder for the electrons to pass by them without colliding. So when they're cold, it'll be quite easy for the electrons to get through. But when they're hot, it's much more likely that they're going to collide with the particles in that solid. And if that happens, it slows the electrons down. If it slows the electrons down, there's less current, so that just means the resistance is higher. Okay, so here the particles vibrate more, so therefore we get more collisions between the electrons and the ions that make up the lattice of the solid. Meanwhile, here we will get less collisions. So what happens when we turn the voltage up is more electrons flow, and as more electrons flow, there will be more collisions, and as more electrons collide with those ions, as they hit into them, they transfer momentum. That causes the particles to vibrate, which actually transfers electrical energy to heat energy. It causes the wire to heat up, which causes the particles, the ions, to vibrate more, which makes more collisions happen, which makes it more likely that there will be more collisions because the ions heat up and vibrate more. So it's kind of what's known as a positive feedback loop here, really. So let's see how we put that into words then. So when the current or voltage increases, there are more collisions, and that is a key word here, between the free electrons that form the current, and we shouldn't really refer to them as atoms, because once the atoms have lost an electron to become a free electron, we should say it's an ion. So between the free electrons and the ions in the metal filament, these collisions transfer energy, causing the ions to vibrate more, and the metal heats up. The fact that they're vibrating more makes it more difficult for the electrons to pass by. Without colliding, which increases the resistance. Because resistance is just a measure of the opposition to the flow of electric current, which is electrons. More collisions means more resistance, and more collisions causes it to heat up more. So just to recap, at low voltages and current, the flow of electrons is less, there's not as many collisions, they don't transfer as much energy, therefore it's cold, the molecules therefore aren't vibrating as much, therefore the resistance is low. As we increase the current, there's more collisions. That causes more energy to be transferred from electrical to heat energy. It causes the ions, those molecules in the lattice in the metal, to vibrate more. That makes it harder for the electrons to get past, means there's more collisions, and therefore the resistance increases. Okay.